The last few lectures that we're going to have in this section of the class are going to look at wave solutions on a series of different types of waveguides. We're specifically going to look at rectangular waveguide, we'll briefly look at circular waveguide, we'll look at transmission lines, we'll look at dielectric waveguides, we've already looked at parallel plate waveguides, we'll look at fiber optics. And the method for solving these problems are all the same, and we're going to talk a little bit about what that method is today, and we're going to develop a discussion on the waveguide field equations. The main objective is that you guys are aware, you should know, that the x and y components of the field, so E sub x, E sub y, H sub x, and H sub y, can be computed if you have solved for the z components of the fields. And what we're going to do, what you need to be able to do, is you need to be able to apply this knowledge to be able to solve for TE and TM modes. For TE modes, we will solve for H sub z, and then we'll compute the other field quantities, and vice versa for TM modes. There aren't going to be any specific tutorial problems for this lecture, but the tools here are going to be used in each of the lectures that we go in for the rest of the semester. So we're going to limit ourselves for the problems that we're going to look at for the rest of this section of the course, and we're going to limit ourselves to problems where the materials inside the waveguide or that make up the waveguide are assumed to be lossless and charge-free. And we're going to assume that the walls are made of perfect conductors. So inside the waveguides, there's no charge. The only place where charge and current can be is on the surface of the perfect conductors. When we get to the dielectric waveguides, we're just going to have dielectrics, and there won't even be any perfect conductors for there to be charges and currents flowing on. So that means that inside the space of our waveguide, we'll be able to restrict ourselves to solving the time harmonic source-free Maxwell's equations. And of course, we're going to look at the time harmonic Helmholtz equation in source-free media as the equation that we're really going to solve. But we already know that the time harmonic Helmholtz equation is just a restatement of Maxwell's equations. So these are the four equations. The first two equations, the divergence of E and the divergence of B, these two equations give me two scalar equations, and they involve all three components of the field. Whereas the latter two equations are vector equations, and so I really have an equation for the x component, the y component, and the z component in each of these two equations. So this set of four equations, along with the assumption that we're working in Cartesian coordinates, actually gives me 8 equations that I need to solve for. And so we're free to combine those equations in certain ways so that I can express some of these field components in terms of others. And so what we're going to do, or what your textbooks both do, is they manipulate these expressions in such a way so that you can write these 4 field quantities in terms of these 2 field quantities. Right? So we're going to work with the assumption that we're going to solve for E sub z and H sub z. Right? And once we know those 2, we will then compute these other 4. Okay? Now, we've already started to look at the concept of different types of modes. We know that there's TEM modes. These are modes that are transverse electromagnetic. So in that case, both E sub z and H sub z are equal to 0. And this set of waveguide field equations will not be useful. In a TEM mode, I can have E sub x and E sub y without an E sub z or an H sub z. And so we need to use a different method to solve those problems. But for the transverse electric and the transverse magnetic modes that we've already begun discussing, we'll be able to use these tools. So our TE modes, right, we're going to be assuming Z propagation. For all the problems that we're going to do for the rest of this semester, we're going to assume that our propagation direction is in the Z direction. Okay? And so a TE mode will have electric field perpendicular or transverse to the direction of propagation, which means that E sub z is equal to 0. And likewise, my TM modes will have H sub x and H sub y, but they will have the Z component of the magnetic field equal to 0. So that will simplify things even further. Remember, we said we're going to express E sub x, E sub y, H sub x, and H sub y in terms of E sub z and H sub z, but we're going to restrict ourselves to TE and TM modes, so one of these is going to be equal to 0. Now, both of your textbooks go through the entire derivation, and the entire derivation is just algebra. And I don't expect you to be able to reproduce that derivation. You should be able to understand the steps. It's really just algebra with complex numbers. It's tedious. I really have no expectation at all that you could produce it from scratch. However, I do expect that you can use the result, and I have printed up here the result. And I'm going to go through the individual terms just so that you're familiar with what we're talking about. Okay, we are going to use a notation that's just a little bit different than your textbook, and I'm just going to do that for clarity and consistency. So our materials involved have parameters mu and epsilon. Those are the material parameters, okay? This quantity here, beta sub u. Beta sub u is the wave number for a plane wave propagating in this medium. So we're going to use beta sub u to equal, beta sub u is going to equal omega square root mu epsilon. So this quantity here, beta u, is going to equal omega square root of mu epsilon. Right? Beta sub z is the propagation constant in the z direction, and that's one of the unknowns. We're going to need to solve for beta sub z, and we've already looked at this in the context of TE and TM modes on the parallel plate waveguides, as well as the TEM mode and the plane waves. Right? But beta z is going to be a feature of the problem, and how beta sub z relates to omega is going to discuss the dispersion of the object. So these are the set of 4 equations. And the steps to solving a waveguide problem will be to solve Helmholtz equation for either h sub z or e sub z, plug the result into the set of equations, and that gives us the rest of the mode. Right? So it's very straightforward, and we're actually going to do the same thing over and over and over as we look at different types of waveguides for the rest of the class. So the takeaway message, and what's very important that you understand, is that when you need to solve for a waveguide mode, you can describe the entire waveguide mode in terms of either E sub z for the transverse magnetic modes or H sub z for the transverse electric modes. Once you've solved for that z component, you can then plug that into the equations on the previous slide, and that will allow you to compute the other 4 field components of interest for that particular mode. So these are the equations that you need to be able to use. As I indicated at the beginning, there's no specific tutorial questions for this lecture, but we're going to exercise these concepts immediately when we look in the next lecture on the solution for modes in rectangular waveguide when I have perfect conducting rectangular cylinders.